ever wondered why some measurements have only a number while others need both a number and direction? Today, we're delving into the fascinating world of scalars and vectors, the two fundamental types of quantities that describe motion in our universe. The answer lies within the captivating realm of scalars and vectors. Let's explore this with a concise explanation from Physics for Scientists and Engineers by Raymond Serway and John Jewett. Scalars and vectors are two types of physical quantities that describe the motion of objects and the behavior of forces. Scalars are quantities that have only magnitude, such as mass, temperature, and energy. Vectors, on the other hand, have both magnitude and direction, such as displacement, velocity, and force. Scalars are quantities that only have size. For example, a person might have a mass of 100 kilograms. The temperature outside could be 20 degrees Celsius, or it could take you 5 minutes to walk to school. Vectors, however, have both size and direction. You might say you've displaced yourself 10 meters to the east, are moving at a speed of 5 meters per second to the north, or are applying a force of 10 newtons to the west. Scalars are represented as regular numbers like temperature or speed, while vectors are depicted as arrows. The length of the arrow shows the magnitude and its orientation indicates the direction. Consider speed and velocity. Speed, a scalar, tells us how fast a car is moving. Velocity, a vector, also tells us the direction of motion. Similarly, temperature, a scalar, informs us about heat, while wind velocity, a vector, provides speed and direction. To simplify, think of scalars as oranges, measurable only in size with no direction. Vectors are like footballs, they have size and direction. Or imagine scalars as a cup of water, quantified by how much water is in it. Vectors, on the other hand, are like a river. You can tell how much water is flowing and in which direction. When it comes to arithmetic, scalar arithmetic is straightforward. You can add, subtract, multiply, or divide scalars just like regular numbers. For instance, adding the mass of two objects gives the total mass. Vector arithmetic is a bit more intricate. To add vectors, their magnitude and directions need to be combined. Two vectors pointing east add up to an eastward vector, but two vectors pointing in different directions produce a new direction. For example, if one car moves north and another east, their combined directions would result in the northeast. Now let's discuss some graphical and analytical methods for working with vectors. Triangular law: imagine two vectors as sides of a triangle. The third side is their resultant. Parallelogram law: draw vectors as adjacent sides of a parallelogram. The diagonal gives the resultant. Component method: break down vectors into horizontal and vertical components. Add these to find the final vector's magnitude and direction. Subtracting vectors is like adding their opposites. The graphical and analytical methods apply similarly, but you reverse the direction of the subtracted vector. Historically, the terms vector and scalar were introduced by William Rowan Hamilton in the 19th century. By 1835, Hamilton used vector for directed line segments, and modern vector calculus emerged in 1884 through Oliver Heaviside and Josiah Willard Gibbs. These concepts aren't just limited to physics. Scalars help measure quantities like temperature and pressure, while vectors are crucial in designing structures or guiding pilots. They also play a vital role in understanding weather conditions, like wind direction and speed. Did you know that James Clerk Maxwell, the physicist behind electromagnetism, was also a talented artist? His visualizations of vector fields greatly influenced his groundbreaking equations, which remain pivotal in physics today. For beginners, I highly recommend exploring this book for a deeper understanding of vectors and their applications. Keep your curiosity burning bright.